Hello and welcome to this third lecture on characteristics of discrete time systems. Well, what we've done till now is we have seen how the input discrete time signal is sampled from a continuous time signal and the different characteristics of these discrete time signals. And now these signals if they would be applied to discrete time systems, where a discrete time system is a system where you give a discrete time input signal and you get a discrete time output signal. Okay, then let's see what happens in case of discrete time systems. Now, a system that takes a discrete time signal as an excitation to produce a discrete time output system is called as a discrete time system. So conventional purposes, we use xn as the discrete time input signal, giving output signal yn. Now, before we see what the output yn would be to a discrete time input signal xn, we have to understand a few characteristics of these discrete time systems. Only then we will be able to derive a relationship to get the output yn. Now, what's the first such characteristic that we can study? It's time invariance. Now, it says that a system is called time invariant or shift invariant only if, now if you give xn as the input, the output is yn. So if I give xn minus k the input, assume the output is y1, and this y1 should be equal to y of n minus k. Mathematically writing it is xn if in xn as the input is giving the output yn, x of n minus k as the input should give the output y1, which should be equal to y of n minus k. So you get yn minus k by replacing n as n minus k in y of n. Go to the next slide again. The examples of time invariant systems. Let's take y of n is equal to n into xn. So if xn is given, the output is nxn. If x of n minus k is given as the input, the output would be x of n minus k, because now x of n is not there, it is replaced by x of n minus k, and remains as it is. So this output is considered as y1. Now we have to calculate y of n minus k. Y of n minus k, it will be from yn is equal to nxn. So y of n minus k replacing n minus k. So you have n minus k here, n minus k here. Now we observe that y1 and y of n minus k are both different. So therefore this yn is time variant system, or the signal is time variant signal. Another example. Okay, this time we go to linear and non-linear discrete time systems. Now, in the case of linear and non-linear, how do we consider linearity? Well, the definition is a bit too long. In fact, response of the system to a weighted sum of signals should be, so if you have a weighted sum of signals, say x1n and x2n multiplied by weights a1 and a2 should be equal to the corresponding weighted sum of the outputs. So that should be equal to a1 y1 and a2 y2 of the system to each of the individual input signals x1 and x2. So let's see, mathematically it will be more clear. In fact, before that we'll show you a graph. Okay, it's called as the superposition principle, because all the weights go on superimposing on the discrete time system. So like you have a discrete time system, x1n multiplied by a1, x2n multiplied by a2 are both superimposed in the signal to get yn. This should be equal to x1n giving y1n, x2n giving y2n. So it will be a1 y1 plus a2 y2 giving me y of n. Now how do we do this mathematically? So how do we check this linearity? So let's take an example. Y of n is equal to x of n is given. So what do we do here? We assume two steps. y1n is equal to x1n, y2n is equal to x2n. Then the third step, the important step, we can assume x3n as equal to a1 x1n plus a2 x2n. You assume this. So from this, knowing x1, x2, we know y1, y2. So knowing x3n, you have to calculate y3n. Now in this case, y3n is pretty much simple. y3n is equal to x3n, which is a1 x1n plus a2 x2n. This is step number 1. And step number 2, what you have to do is you have to calculate value of a1 y1n plus a2 y2n. Now only if 1 and 2 are equal, then we say that a system is a linear system. So in this case, yes, y1n is x1n, y2n is x2n. This and this appear similar, so therefore it is a linear system. Examples: y of n is equal to x of n squared. Now, so what do we do? Immediately assume these two, y1n, y2n. We know how to assume this. Also assume x3n is equal to a1, always assume x3n is a1 x1n plus, if there are two constants, if there are 3, you can take 3. Okay. Now, so y3n is x3 of n squared, because if this is x1 of n squared, this is x2 of n squared, so y3 of n is x3 of n squared. So how do you get x3 of n squared? Simple functions. x3 of n given, n squared replace n square, n square, n square. y3n is equal to a1 x1 n square plus a2 x2 n square. This is penultimate step. The last step would be calculating a1 y1n plus a2 y2n, which would be a1 x1 n square. Just take the value of y1n from top over here, y2n from top over here, and you get a1 y1n plus a2 y2n, which is nothing but y3n, and hence you get a linear system. Okay, I think we have just one more example. Say y of n is equal to x square n now. So here again x3n, you assume this, but here y3n is x3 square n. So it is nothing but a1 x1n plus a2 x2n the whole square. At the same time, here you have got a1 y1n plus a2 y2n, which is a1 x1 square n plus a2 x2n square. Therefore, obviously, y3n is not equal to the linear combination of y1 and y2, and hence this is a non-linear system. Next property of discrete time system is the causality. Now, when would you say it is a causal system? A causal system, if the output of the system at any time instant n depends upon only the present and the past inputs, this xn, xn minus 1 and so on, and does not depend on the future values, x of n plus 1, x of n plus 2, future values of x of n plus 1, x yet to come, so they are future values, then they are said to be a causal system. Let's take examples. Y of n is equal to x of n plus n, x of n plus 1. The minute you have a future sample, it's a non-causal. Next one, y of n is equal to x of 2n, non-causal, because n equal to 1 will give y of 1 is equal to x of 2. Non-causal. Obviously, this is only n causal. Y of n is equal to x of minus n. So if I say n equal to 1, x of minus 1, no, x of minus 1 will give you x of 1. So again, non-causal. N square also 2, n equal to 2, you get x of 4. So again, non-causal. So the system is said to be non-causal if the output of the system depends on the present, past, and the future. So here, what you have to see is that the signals which exist for n equal to 0 and n greater than 0 are causal, and less than 0 are not non-causal, and less than 0 will be anti-causal. And therefore, if we have systems, if you have signals which are dependent on past, present, and the future, that means on the left hand side as well as on the right hand side, then they are called as non-causal systems. Now, having understood these properties, we would then go to understand the response of the system to a discrete time input signal. Thank you very much.